Hello there, ATSEVS533 students. Dr. John Schrage here with another lecture to you from the first module of our course. Now we are beginning to work a little farther into the IPCC report. And like I said before, I get it that that is not a thrilling read. That's okay. It's part of the vocabulary of being an environmental scientist to understand how these kinds of summary reports are written and how to find the information that you need in there. So I'm not kidding when I tell you, you do need to do those readings, okay? And if you haven't done the reading for this lecture, pause the lecture and go do it now. Okay, if you're still with me, on the other hand, it's time to move forward with some of the stuff about observations of climate change that we are seeing in Chapter 2 of our textbook. And at the present time, we're going to focus on measures of temperature. Now, that at first might not seem like that's all that big of a surprise. I mean, we know that part of what we're going to be looking for is global warming, and in particular the ways in which humans are enhancing the greenhouse effect. Now, but that also puts a lot of burden then on the climate scientists to make sure they're doing the temperature observations correctly, and that we know what they mean, and that the observations are homogeneous. We'll learn what that word means in a little bit. But this makes sense that this would be the observation that we want to spend the most time on understanding, because obviously temperature is the variable that is most directly affected by the addition of greenhouse gases. Addition of greenhouse gases is going to do other things too, like potentially change the wind distribution, or change the humidity distribution, or change rainfall, or whatever, but certainly what it is most directly affecting is the temperature. As it happens, we also have the best available data when it comes to temperature as well. Temperature is something that can be measured really accurately, really consistently, very cheaply, and has been done so for a very long period of time. I mean, good old Daniel Fahrenheit, back in, I don't know, like the 1600s in Holland, invented the liquid in glass thermometer that we know and love. There were other kinds of thermometer technologies like the Galileo thermometer before then, but that's not really a scientific instrument. The actual invention of the thermometer happened a really long time ago, and it's a really reliable piece of technology. We can use it really well. In some of my other classes, we actually get into the details of why this is such a easy to use piece of technology, and in some ways it was the right tool at the right time. Because right about the time that the thermometer became something that learned men and women wanted to work with and understand and use in a scientific way, is about the time that Western explorers and Western merchants and so on started spreading this kind of technology all around the world. And it became very much the case that if the French were setting up a colony in Polynesia, one of the things they needed to do was set up a weather station there where they were observing the temperature. And to be honest, they were pretty good at it, okay? These temperature observations that we have from surprisingly far back are remarkably well calibrated and remarkably consistent and so on. Temperature also has the advantage of being a climate parameter that we can extract information about the past from. That's probably not a very articulate way of saying it. We can use paleoproxies to understand the temperature of the past. Like, for example, corals. Okay, we haven't yet learned this word paleoproxy, but my guess is you understand this word paleoclimate and how we can study and understand the climate of the past even before we had thermometers. Okay, we can do things like dig corals, a core through a coral reef, and learn about the temperatures that that coral reef was experiencing in the past. Or we can dig ice cores and learn about the temperature conditions in the past at that location. There are paleoclimate ways to understand rainfall as well, or wind distributions or so on, but definitely they are not as clear of a signal, not as unambiguous of a signal as our temperature records in the past were. So temperature tends to be what we want to focus on when we are discussing temperature. Now, we mentioned before, though, it is kind of tricky and complicated to describe climate change in terms of the actual absolute temperature directly. Of course, we're going to need to be working with temperature anomalies. I'm only bringing that up now because sometimes students kind of gloss that over in that, wherever it was either the first or the second lecture when we talked about that in the past, thinking, oh, this won't come back up again. Yes, it will. All semester long, we're going to be looking at plots and so on in terms of temperature anomalies. That is to say, the difference between the absolute temperature being measured and some kind of reference temperature, which is typically the 30-year climatology at that location. So, where do we get all these temperature observations that are going to be telling us something important about both current climate and climate change and so on? Well, setting aside things like paleoclimate records and so on, which we will talk about on a different day in this module, let's focus on current observations that we are getting as part of the routine monitoring of the planet. These observations are usually taken for meteorological purposes, like flight operations or public safety or agricultural purposes. But clearly we can use these observations of temperature, and for that matter rainfall and visibility and wind and all that kind of stuff too, to talk about climate. Now, almost any science class is going to talk early on about how there are different philosophies of observation and how there are two main types of ways that you can take observations of the world around you. One is going to be the so-called in situ observations. In situ is a Latin expression that means something like right here, right now, or on this spot, or whatever. And an in situ observation strategy is when you can, the instrument that you are using to take the observations is actually touching what it is measuring. So, for example, when you're sick and your mommy puts a thermometer in your mouth, it is measuring the temperature inside of your mouth. When the thermometer is in the drawer, it is measuring the temperature inside the drawer, not inside of your mouth. It is measuring what it is touching. A barometer measures the pressure of the air that it is touching. An anemometer measures this, as the thing with the little cups that spin, that is measuring the wind speed of the air it is touching. We launch weather balloons that carry packages of instruments up into the atmosphere to collect in situ observations. The instrumentation package is touching the air that it is measuring. That is in contrast to a remote sensing observing strategy in which the instrument that is doing the measuring is not actually touching what it is measuring. In the context of like earth science and atmospheric science and climate science and so on, we're almost always talking about things like satellites in that case, where the satellite is measuring properties about the earth, like soil temperatures or leaf area or winds or whatever, wave heights and so on, without actually touching the waves or whatever. Okay? More broadly, remote sensing techniques could be things like telescopes, for example. A telescope is measuring something far away from the instrument itself. In situ measurement of the atmosphere is something that meteorologists do, and in fact, we routinely do that all around the United States and frankly all around the world as well. Just to give you a sense, here on this map of the United States, every place there's a little red dot there. That is that's a location of an official weather station run by either the National Weather Service or the Federal Aviation Administration. These are two organizations that have different mandates. FAA is primarily doing it for aviation safety. The National Weather Service is primarily doing it for like agricultural purposes, public safety, and so on. But they work together to operate a network of weather stations. Just so we're clear about this word station, this is not like as in TV station. This is as in stationary, as in it's not moving. Okay, think more like train station or something like that. In practice, most weather stations in the United States that are part of this network are at airports. Okay, just because that's a place where, again, there's a legally binding reason why we have to take observations there anyway in order to be part of like the World Meteorological Organization and for international flights to land and so on. So you can see that there are a lot of weather observations around the United States. In fact, if I zoom in a little bit here, just to give you a sense, I think in Nebraska there's about 45 official National Weather Service or Federal Aviation Administration weather stations. These sites, okay, it says here it's actually run by either the NWS or by the FAA. They are typically, although not always, unmanned. Some weather stations are co-located with things like a regional National Weather Service office, and there are in fact forecasters and met techs, meteorological technicians and interns and so on who are working there and monitoring the equipment and so on. But by and large they are an unmanned set of instruments, like I said, typically co-located with an airport. So here's a typical picture of some of them. It's a cluster of meteorological instruments that takes official National Weather Service or FAA weather observations. Typically these instruments are designed to take the observations once an hour. If something is happening in the weather, like a line of thunderstorms is moving through, they can be programmed to take observations more often, but by and large they take the observations once an hour. Just to kind of give you a little tour here, you can see that at the top of a mast there is a set of sensors that are measuring the wind. There's an anemometer, the thing with the little cups that spins. There's a wind vane, that thing that points the direction of the wind. There's a set of sensors here that measure the visibility. These are actually really cool, but don't have much climate application. But for in terms of theory of instruments in meteorology, it's actually really cool how they work. And it makes sense that you would need instruments that measure the visibility at an airport, because that's obviously one of the most important pieces of information a pilot wants. There are sensors that are measuring the temperature, and it might be a little hard to see, but see how there's sort of a little shed kind of thing there? It's called a shelter, actually. It kind of looks like a little bit like a birdhouse. If you actually go and take a look at it, you can see that it's actually kind of like a little louvered box. See how air can flow in through the sides of this box? The box provides shade. It's in fact a very bright white box, so it reflects sunlight and so on. Because official National Weather Service approved observations, in fact all observations that get the seal of approval of the World Meteorological Organization, must be taken in the shade. If you take weather observations, temperature observations in the sun, with the sun directly shining on the thermometer, the temperature that the thermometer is reading is partly about the radiative balance it's coming into with the sunlight and so on. You need the thermometer to be in the shade. And so typically they're inside of these sort of little boxes like this. Generally speaking, like I said, these stations are unmanned, although a key feature of them is that professionals do keep the thermometers and the other pieces of meteorological instruments calibrated. They actually visit them routinely. I know I've had questions in the past as to how often they come and visit. It's certainly on the order of every week or two. They come out, meteorological technicians actually check to make sure all the instruments are in working order and are not damaged in any way. You can well imagine that birds and things sit on it, poop on it, whatever. They have to clean it all up and make sure that the observations are high quality all the time and that they are calibrated. Just in case this word calibrate is something that you only have kind of an intuitive sense of, you didn't know a dictionary definition of the word calibrate, just to pull out a card here from Google. I like how calibrating is correlating the readings of an instrument with those of a standard in order to check the instrument's accuracy. So they will, let's just say, for example, they might put the thermometer into an ice water bath. Okay, ice water has a temperature of exactly 0 degrees Celsius. So they make sure the thermometer reads 0 degrees Celsius when it's in there. And there's other kinds of controlled ways to calibrate the different instruments. So it's these meteorological technicians' job to keep the temperature observations as precise and accurate as possible. Excuse me. This is something that is mandated by the World Meteorological Organization. You can't just set up a weather station and let it continue to radio observations. I mean, some kind of instrument here is then transmitting these observations back to your National Weather Service office and so on. You can't just leave the instrument out there for years on end unattended. They must be calibrated and so on, routinely maintained and so on. Now in the United States, in addition to the network of observations that we get from the National Weather Service and the FAA, there's a whole network of what are called cooperative weather observers. Cooperative weather observers are just people like you and me. They get a little bit of training, like an online one-day class or something they do on, they read a book or watch a video or something. And basically, the Cooperative Weather Observing Network then issues them a special kind of little weather station, we'll see some examples in a little bit, that just records not like the hourly temperature and the hourly winds and so on, but just daily values like the daily high temperature and the daily low temperature and the 24-hour precipitation and so on. And so at least we have some way of monitoring the weather at a larger number of locations. And in fact, if I just sort of pulled up, this is just from a website here, where you can see all the locations in eastern Nebraska of cooperative weather observing stations. Well, you'll probably have to actually kind of squint to see Omaha and Lincoln and so on there. I mean, there's hundreds of these. I think there's about 600 cooperative weather observers in Nebraska alone. There's tens of thousands nationwide. So again, we have another whole source of information that is independent of what the National Weather Service does. You can see how this Cooperative Weather Observing Network has sort of a mandate to kind of provide an independent source of information over what the Weather Service and the FAA is coming up with. You can become a cooperative weather observer. All you got to do is complete the little online course or watch the necessary videos, and you too could be a cooperative weather observer. Tons of people do it. Alright, before we move forward and talk more about temperature observations, let's answer 3 quick questions. Question 1. All weather stations are manned as required by the World Meteorological Organization. True or false? Make a choice from those 2 options and get a little feedback before you move on to the second question.